Welcome to our game development tutorial series. Today, we are delving into the exciting world of 2D games by learning how to create dynamic mazes using Unity, C#, and the backtracking algorithm. Mazes have long been a staple in video games, offering players a challenging and immersive experience as they navigate through winding pathways and hidden corridors. And now, with Unity, you can bring these intricate mazes to life in your own projects. In this tutorial, we will take you through the step-by-step process of generating mazes in Unity2D, from setting up your project to implementing the backtracking algorithm for maze generation. By the end of this video, you'll have the skills and knowledge to create captivating mazes that will keep your players engaged and entertained. Go ahead and create a new Unity2D project, naming the project MazeGen. Once Unity is loaded, rename the default sample scene as scene_maze generation. We will first create a room prefab. We will use this prefab as a unit cell in the 2D grid. For this tutorial, we will keep things simple. We will create a room that is made up of 4 walls. Right-click on the scene hierarchy and create a new empty game object. Rename it to Room. Select this game object and then add a new 2D square sprite. Resize it to have a length of 5 units and a height of 1 unit. Change the transform's position value with X as 0 and Y as 3. Rename this sprite to Top. Now, duplicate this sprite and change the position to Y as -3. This change will relocate it to the bottom. Rename the sprite to Down. Similarly, now add another 2D square sprite. This time, resize it to have a length of 1 unit and a height of 5 units. Change the transform's position value with X as 3 and Y as 0. Rename this sprite to Right. Now, duplicate this sprite and change the position to X as -3. This change will relocate it to the left. Rename the sprite to Left. After that, create 4 more 2D square sprites for the 4 corners, each of size 1 unit. Rename these 4 sprites to corner_left top, corner_right top, corner_right bottom, and corner_left bottom. Change their positions to X as -3 and Y as 3, X as 3 and Y as 3, X as 3 and Y as -3, and X as -3 and Y as -3 respectively. We will now add the floor of the room by creating another 2D square sprite, resizing it to 7 and 7 and setting the Z value to 1. Change the RGB color of the sprite to 150, 150, and 150. Select all the wall and corner sprites and change the RGB color to 200, 200, and 200. Go to the project window and create a new folder called Scripts. Add a new script called Room in this folder. Add this script component to the Room game object. Double-click the Room script and open it in Visual Studio or your favorite editor. This script's main purpose is to control and manage the visibility of walls in different directions and enable the creation of a continuous walkway for the maze. We start with defining an enumeration called directions. This will help us identify the different directions our walls can face: top, right, bottom, and left. We declare some serialized fields of type GameObject to represent the walls in each direction. These fields will be assigned in the Unity editor. Next, we create a dictionary called Walls, which maps each direction to its corresponding wall GameObject. We then implement a property called index of type vector2int. This property will store the index of the room in the game grid. We also add a Boolean property called visited, which indicates whether this wall has been visited or not. By default, it's set to false. Another dictionary called direction flag is used to store the flag indicating whether each direction's wall is active or not. In the start method, we populate our walls dictionary with the assigned game objects for each direction. This allows us to easily access and manipulate the visibility of walls in different directions throughout our game environment, providing a convenient way to control the state of individual walls based on their direction. We then define a private method setActive that takes a direction and a Boolean flag indicating whether to activate or deactivate the wall in that direction. Finally, we implement a public method called setDirectionFlag, which allows us to set the flag for a specific direction's wall and update its active state accordingly. This method will be called by the maze generator later when we implement it. Now, go to the Unity editor and select the room game object. After that, associate the wall game objects with the correct script wall field in the inspector. Go to the project window and create a new folder called Resources in the Assets folder. Go inside the Resources folder and create a new folder called the Prefabs. Drag and drop the room game object inside this Prefabs folder to make the room a prefab. We shall now start with the maze generation process. For this, create an empty game object and name it Generate Maze. Create a new script called Generate Maze in the Scripts folder. Drag and drop this new script into the Generate Maze game object. Double-click the script and open it in Visual Studio or your favorite editor. We add a variable called the room prefab. This variable will hold the prefab of a single room in our maze. We then add the 2D array of rooms. This variable will represent the grid of rooms where our maze will be constructed. Then we add the variables that will determine the number of rooms along the X and Y axes of the maze grid, respectively. They will define the size of our maze grid. After that, we add two float variables, room width and room height. These variables will store the width and height of each individual room in the maze. We will calculate these values based on the dimensions of the room prefab. Now we add a stack data structure that we will use for backtracking during maze generation. Finally, we add a Boolean variable called generating that will indicate whether maze generation is currently in progress. It will be used to prevent the initiation of a new maze generation process while one is already underway. We will now implement the getRoomSize method. This method is responsible for determining the width and height of the individual room prefab that will be used to construct the maze. We begin by obtaining all the child sprites of the room prefab using getComponents in children method. We then initialize two vector3 variables, minBounds and maxBounds, to positive and negative infinity, respectively. These variables will be used to store the minimum and maximum bounds of the room prefab. Next, we iterate through each child sprite obtained earlier using a for-each loop. For each sprite renderer, we update the minBounds and maxBounds variables using vector3.min and vector3.max functions to ensure they encapsulate the entire bounds of the room prefab. After iterating through all child sprites, we calculate the width and height of the room prefab by subtracting the minimum bounds from the maximum bounds along the X and Y axes, respectively. These values are stored in the room width and room height variables. Next, we implement the setCamera method. This method is responsible for positioning the main camera in a way that ensures the entire maze is visible within its view. First, it calculates the position based on the dimensions of the maze grid and the size of each individual room. It positions the camera at the center of the maze grid, slightly adjusted to ensure that it captures the entire maze. After that, it determines the minimum dimension of the maze, either the total width or height, and sets the orthographic size of the camera accordingly. This ensures that the entire maze fits within the camera's view, with a little extra padding around the edges for better aesthetics. Next, we implement the start method. This method is called when the script is initialized, typically at the beginning of the game or when the object containing the script is enabled. We first call getRoomSize to calculate the size of each room in the maze based on the dimensions of the room's sprites. Then we initialize the 2D array rooms to store references to each room in the maze. Next, we use a nested loop to iterate through each grid position in the maze, with num_x rows and num_y columns. Inside the loop, we instantiate a room GameObject at the calculated position based on the grid index, I and j, and the size of each room. We set the name of each room GameObject to indicate its position in the grid. We retrieve the room component attached to each instantiated room GameObject and store it in the rooms array at the corresponding grid position. Finally, we call setCamera to position and adjust the main camera to ensure the entire maze is visible within its view. We now implement the removeRoomWall method. This method is responsible for removing a wall of a given direction from a specified room in the maze. In this method, we first set the flag of the wall in the specified direction of the room at position x, y, to false, indicating that the wall should be removed. Then, based on the direction provided, we determine the opposite direction from which we will remove the corresponding wall in the adjacent room. Using a switch statement, we check the provided direction and update the opposite direction accordingly, considering the boundary conditions to avoid accessing out-of-bounds array elements. For case top, it checks if the given room is not at the topmost row of the maze. If true, it sets the opposite direction to bottom and increments the y. For case right, it checks if the given room is not at the rightmost column of the maze. If true, sets the opposite direction to left and increments the x. For case bottom, it checks if the given room is not at the bottommost row of the maze. If true, sets the opposite direction to top and decrements the y. For case left, it checks if the given room is not at the leftmost column of the maze. If true, sets the opposite direction to right and decrements the x. This method could be very error-prone. Pay special attention to the boundary conditions. Finally, we call the setDirectionFlag method of the adjacent room to set the flag of the wall in the opposite direction to false, effectively removing the wall between the current room and its adjacent room in the specified direction. Now we shall implement the function getNeighborsNotVisited, which is responsible for finding neighboring rooms that have not been visited yet. This function takes in two parameters, cx and cy, representing the x and y coordinates of the current room. Next, we initialize an empty list named neighbors to store the neighboring rooms that have not been visited. We then loop over each direction using a for each loop and the enum.getValues method to get all possible values of the directions enum. Inside the loop, we declare variables x and y to represent the coordinates of the neighboring room, initially set to the current room's coordinates. For each direction, we use a switch statement to handle the different cases. In each case, we calculate the coordinates of the neighboring room based on the current room's coordinates, and then check if the neighboring room is within the bounds of the maze and whether it has been visited or not. If the neighboring room meets the criteria, we create a tuple containing the direction and the room and add it to the neighbors list. We do this for all the cases. Be very careful while implementing this function. It is very error-prone. Finally, we return the list of neighboring rooms that have not been visited yet. We will now proceed to implement the generate step method, which plays a crucial role in maze generation. Within the method, we start by checking if the stack of rooms is empty. If it is, it means that we have explored all possible paths, and we return true to indicate that maze generation is complete. We then peek at the top room in the stack to examine its neighboring rooms. Next, we call the get neighbors not visited method to find neighboring rooms that haven't been visited yet. If there are unvisited neighboring rooms, we randomly select one of them. We mark the selected neighboring room as visited and remove the wall between it and the current room. Finally, we push the selected neighboring room onto the stack for further exploration. If there are no unvisited neighboring rooms, we backtrack by popping the current room from the stack. At the end of the method, we return false to indicate that maze generation is still in progress. After this, we will implement the create maze method. Inside the method, we begin by checking if maze generation is already in progress. If it is, we simply return without doing anything. Next, we call the reset method to reset the maze's state. This involves marking all rooms as unvisited and resetting their walls to their default state. We have not yet implemented this method. We then remove the bottom wall of the bottom left room to ensure there's an entrance point to the maze. Similarly, we remove the right wall of the top right room to ensure there's an exit point from the maze. We then push the bottom left room onto the stack to be the first cell in the maze. Finally, we start the maze generation process by invoking the coroutine_generate method as a coroutine. This allows us to visualize the maze generation process step by step. We now move on to implement the coroutine. This coroutine is responsible for controlling the maze generation process. We start by setting the generating flag to true, indicating that maze generation is currently in progress. We initialize a Boolean variable flag to false. This flag will be used to determine whether maze generation is complete. Inside a while loop, we continuously call the generate step method until the flag becomes true, indicating that maze generation is complete. After each iteration, we yield wait for seconds with 0.05 seconds. This pauses the coroutine for a short duration, allowing us to visualize the maze generation process step by step. Once maze generation is complete, we set the generating flag back to false. We shall now implement the reset method. In this method, we iterate through the nested for loop and sets the flags of all four walls, top, right, bottom, and left, to true, indicating that they are intact. Additionally, we also reset the visited flag of each room to false, indicating that the room has not been visited during maze generation. Finally, we implement the update method where we check if the spacebar key is pressed. If the spacebar is pressed and the maze generation is not currently in progressive, call the create maze method. This allows the user to trigger maze generation by pressing the spacebar key while ensuring that maze generation does not overlap if it's already underway. We will make one final change in our code. We will add a direction of type none in the directions enum. Go to room script and add a new direction of type none. This enum type is required to handle special cases of entry and exit. After that, open the generate maze script again and make changes to adapt to this new direction. Go to the remove room wall method and check for none direction enum. If the direction enum is none, then do not call the set direction flag. Set the default value of opposite direction as none. Then if the direction enum is none for the opposite direction, then do not call the set direction flag. By doing so, we are handling the boundary cases for wall removals. Now, go to the Unity editor. Select Generate Maze Game Object from the hierarchy. Go to the inspector and associate the room prefab field by dragging and dropping the room prefab from the prefabs folder. Click play and press the spacebar. See the maze generation in action. Press the spacebar again to recreate the maze. You can also change the grid size in the inspector and test it out. And that's it. We have implemented our dynamic maze generation in Unity2D using the backpropagation algorithm. In the next video tutorial, we will enhance the maze generation with some more visual representations and then apply pathfinding within the maze. Till then, happy coding!